Thank you, Chair. Yeah, it's a real honor and privilege to be asked to be the last voice standing. It's a real pleasure being here. Obviously, coming back to your country of origin is a pleasure, but to this workshop specifically. I sort of participated in this workshop 2 years ago. I couldn't travel out of Aotearoa, New Zealand, to be there in person. So I contributed a recorded presentation, which is just not the same, right? I mean, you're sitting in the office talking to a screen. There's absolutely no interaction. So I thought, okay, this is an opportunity to basically revisit some of that or the topic that I talked about at that workshop. A lot has happened in the meantime, and this is the opportunity for a face-to-face discussion around the topic, right? It's also the app that we're following kind of a collaborations session in terms of what's the recent collaborative research opportunities that we can explore. I also realized the challenge with being last in the program in that I hope I don't repeat too much of what some of the presentations have already talked about, because we've really heard some really good presentations, really excellent research over the course of these two days. Yeah, so our interest is one of the topics that we are interested in my group. I head up the Sustainable Energy Systems group in the Wellington Faculty of Engineering. And New Zealand has this green image. It's not really that green, but anyway, it has this green image. But we realized that we are actually outsourcing a lot of that. And so understanding what the material intensity is important for us. When Biagio sent me this email that said you have 50 to 60 minutes, like Mark Swilling said yesterday, that's refreshing. But I'm not going to have a monologue here for 50 or 60 minutes, right? So I'm going to share with you some of our perspectives of what we see some of the challenges are in the world today in terms of the materials for our just transition to a net zero economy, global economy, but also singular economies. But here I think we should have a dialogue. Dialogue that goes wider than maybe just this topic. I'm not going to dwell on too much. I actually hit the slides before, but anyway, so our group has been around since 2017. We're a core of six people, but we collaborate with other faculties across our university and with other universities in New Zealand, because yeah, the just transition is a transdisciplinary challenge, right? So it's not only up to engineers to solve. So the net zero, the transition to net zero economy, as we've heard over this 2 days, and as this community knows, it's a lot of it is about energy. And in the last 6 years since I started this group, things have changed somewhat in the energy sector. Back then, they talked about the 3D trends in the energy sector. In the meantime, we've added another 3. So we all know we need to decarbonize, or as Mark said, low carbon energize. Right, we are talking about decentralization because Jana Brent was discussing this previous vertical for the electricity system, energy sector wide. We sort of had this vertical integrated systems. Now we're going the more horizontal, we're moving things out. People are becoming more self-sufficient and resilient, and I want to talk about that later on. We all know about the concept about the smart grids and so on, and using the Internet of Things and so on. So it's all about digitalization. So those are the 3 Ds that we talked about 6 years ago. But now, in the meantime, it's just. Okay, so that's why I was putting the democracy there. That's what we mean, just. We need to empower people and communities to take charge of their own energy. Is disruption because not only from a technology perspective, we have new technologies coming in, it's also disruption because of behaviors of people. So we'll talk about electric vehicles and so on in a moment, but just as an example. And then there's diversity. So it's, yes, we want to electrify the economies, but we have different options for that. So we have diversity of technologies, we have diversity within our society of how the energy is used, and we need to cater for all of them. So, especially around demand, how demand is changing, and as I said, behavioral change is important. So our energy system needs to be adaptable to some of this disruption, diversity, and doing it in a just way. And this means that it's actually becoming more complicated and complex. So this is a report that the National Renewable Energy Laboratory brought out, must have been 2 years ago now. This is obviously more US focused. Yes, it's complicated because we need to integrate grids. They have a challenge over there that in different states, or they have smaller transmission systems that don't talk to one another. So they talk about those technical challenges, but it's also what's happening inside. The grids becoming more complicated, but it's also complexity because there is certain unintended consequences that's happening within the energy sector, and obviously, as we all know, climate change is an additional challenge. So where we are in our part of the world, yes, it's fantastic. We're 85 to 90% renewables now in our grid, but it's largely based on hydropower. And so we're really worried about dry years and how we're going to adapt to that. And as we all know, these are the scenarios that NREL came up with for the US. We're just getting more variability. We have more options for storage. As Mark and I was discussing as well, the one danger that you see in this slide is they talk about where's hydrogen. Hydrogen is there, the green dot over there. They talk about hydrogen as a source. It's not, right? It's just the energy vector. So it's another storage option. So there's multiple storage options that are available to us, not only the classic batteries, hydrogen is a storage option. There's biomass, there's gravity storage, there's liquid air. It's just the amount of innovation that's going into the space is quite unreal. But the point out of this is a lot more diversity, as I said before, in terms of the sources that we can use, the storage options available to us, etc. Enter microgrids. So 2 slides in terms of looking at microgrids. This is one. Says, okay, we're going to be growing, we're going to be doubling the market around microgrids in the world in terms of US dollars. Another study, this is good. Has put a figure up to about $80 billion. So microgrids are becoming more important, and for various reasons. So in Asia, it's really grown. Africa is somewhat growing because of rural electrification or remote areas. That's also important for us in our neck of the woods because of our island communities. But interestingly, the biggest market for microgrids is in the US. Okay. This goes back to what I was saying with climate change, is that you run the danger of the main grid falling over, so you want your communities to be self-reliant. So it's really taken off in the US. And these microgrids are on the left-hand side. If you're in the microgrid space, you know that is the classic example. It's Brooklyn community in New York. That has been running for a number of years. And it started off as just distributed solar PV and batteries within the community. On the right-hand side is a microgrid that we worked on for Stewart Island. And what that shows is it's becoming a lot more complicated. Some PV panels, because Stewart Island is below our South Island, so it's not really good solar resource, but it's good wind. But it's agricultural community, so we can look at agricultural waste. You'll see in the mix there is hydrogen as well, because they're looking for hydrogen for the ferries and some of the agricultural equipment. It's also being electrified, more EVs that get integrated there. It's becoming what we call the grid of grids. All right, so in this case, yes, on the right-hand side, an isolated remote community. On the left-hand side, that's an integrated community. it's connected to the grid. So that just leads, what that means is just a lot more complexity, as I said before. And a challenge in terms of how to optimize. We're working now on each one of these microgrids will have its own electricity market, small electricity market, where people are selling electricity, selling the demand response, storage, using the EVs as an example. And so, yeah, very similar to what we see in a liberalized macro wholesale market, but honing in down to the microgrid level. And we have one study at the moment where we have 2 microgrids in New Zealand and trading between them over the national grid. So, and communication, technology, and so on, technologies are enabling this. But the point for today's discussion is a lot of diversity in the components that we're actually using for these grids. So taking one step back, and these are figures from International Energy Agency. So it says solar and wind is going to be the big, in terms of source, to a large extent. So solar wind, we're going to see about 3 times capacity in the next 2 decades. Wind similarly. On the right hand side, we all know what's happening with the EVs. Okay, so we see about a 25-fold increase in that, and we can have a whole discussion about what to do with very heavy transportation. We have imported the first hydrogen trucks into New Zealand. We're busy building the first refueling stations, but that's also a debate we had. And importantly for me is the middle one. Discussions we've had last week at the energy conference, Nelson Mandela, and discussions I had with colleagues here in the last 2 days, is the grid is insufficient to handle all of this disruption. It's not capable of handling this variable renewable resources, batteries, EVs coming onto the system. So we need a lot more investment in our backbone and so on. And it needs to be expanded, and all the associated power and electrical components that go along with that. But that's on a global level. I mean, each country needs to look at its own. So this is work that we did for Artery in New Zealand. Dashed line there is our projected demand going forward in the next 3 decades. We have a target of getting rid of all of our fossils by 2030. And as I said, we're on track to do that. And we are not thinking about increasing hydropower too much. There's one project of pump storage that is being investigated. But hydro, there isn't an appetite for large-scale projects from an environmental perspective. So geothermal, we're looking at expanding that slightly, but then, again, largely it's wind and solar. At the moment, you can see our current capacity. It's a small annexation of 5 million people, right? So our economy is quite small. So we just have about 100 gigawatts of generation capacity. But we have about 8 gigawatts of solar projects, utility scale solar projects that are in various stages. So about 80% of our new build solar. But small distributed solar is also taking off. That's the part. And we obviously, like the rest of the world, we are exploring offshore wind to order of about 3 gigawatts. So what does it mean? You can see there's a bit of an overbuild that we project, because we need to bring in a lot more storage to deal with that. I'll come back to that later. So what does it mean? There's 2 studies out of Europe with different scenarios. But what you can see over here in terms of the electricity sector, as we're ramping down our fossil fuel usage, you can see that the green mineral component is growing. The electricity sector, transportation sector is just exploding, basically, as we're moving away from our internal combustion engines. As you can see on it. And another study looked at, as an example, we can see steel, aluminium, and some of our other rare earth elements stock really ramping up immensely as we're going into this transition. And it's sort of interesting unpacking. I don't know if you looked at the IEA report that came out 2 years ago about the critical minerals for the transition. Just starting with the car, a conventional car. Yes, you have thousands of moving parts. This is an electric car, electric moving parts. There's a lot more copper in there. There's a lot more nickel in there. There's manganese, cobalt, graphites, rare earth elements, right? It's becoming pretty intensive. So that EV car is the green, really. Same with power generation. You know, if we look at the offshore, so very copper intensive. And we see the rare earth elements coming with permanent magnet drives that we typically use with offshore wind generation. But the same goes with solar PV, where we have obviously the silicon, but we have copper, we have silver, etc. So, point out what you get out of this. If you look at your fossils at the bottom here, they're not really that mineral intensive. But the moment we go into the clean tech, it becomes very mineral intensive. And it's sort of interesting looking at the supply chains as well, because look at oil and gas, it's a limited number of players that we've had over the last century or so. And at the moment we get into clean tech becomes quite disputed around the world in terms of where it's supplied. For instance, lithium, Australia and Chile, copper is obviously Chile and Peru, cobalt, Democratic Republic of Congo. Okay, so it's probably the largest supplier. And we're trying to move away from that, but it's an interesting debate, right? Because there are certain social and environmental issues associated with that production, but it's an important livelihood for the people of DRC. And then also in the processing, China is starting to play the largest role in terms of processing those minerals that start manufacturing the batteries, etc. So a lot more intricate supply chains is what we're starting to see. But it's quite geographically concentrated. So down here where we are, platinum, South Africa is the major player. Lithium is largely Australia and Chile, a little bit in China, but there you see again the rare earths, graphite, and it's concentrated in China. So it's quite geographically concentrated. Which also then means, ever since I started my career, we talked about beneficiation and localization and so on. It's even becoming more important in terms of what technologies do we utilize. This was a report that trade and industrial policy strategies. This is a think tank that informs policy making here in South Africa. Report that they released last month, looking at vanadium, because South Africa is a big producer of vanadium. And vanadium redox flow batteries is an excellent stationary storage option. And this is something that we can capitalize on. So rather than moving minerals out of the country, being processed and buying technologies back, what can we do within our own countries and utilize those resources more effectively? It's also becoming a geopolitical issue, right? This is just an article also last month about restrictions from China in terms of graphite. So that's used in the anodes of batteries, etc. A while back, we also saw that move from the rare earth elements. Right? So countries are becoming strategic to hold on to some of those materials. So it's heating up from a geopolitical perspective. And we saw that in the with, the electronics industry, but now that's also happening with the energy sector. Now, we've heard quite a number of presentations over the last 2 days about life cycle analysis of this community, where we understand there are upstream implications in terms of where it's mined and the energy that goes into that, and the waste material that's associated with that. I didn't hear too much talk about the water implications, okay, the water impacts. But that's a significant issue with obviously the mining, but also the processing of some of those materials. But there's some other challenges in terms of the upstream implications. This was an article, Forbes, I think that was also last month, 20th of October, where Glencore CEO Gary Nagle said, hang on, guys. The amount of copper that you're talking about for this clean energy transition, it means that we will need to mine and produce the same amount of copper over the next 2 decades that mankind has produced until now, over all of history. So this is a major issue. That there's a major copper deficit coming in terms of, again, going back to trading the electricity system, all those transformers and substations that we need to put in there, and also into the energy generation. And the supply of the copper is complicated. The resources are there, right? Talking to with our geologist colleagues, but the time it takes to actually get a mine going and start producing, it is just quite time consuming. Right. So this is the real challenge that we're facing, and copper is the obvious one because we need this large quantities, but it's the same with the other minerals. So that leads us to other sticky issues. All right. So as I said before, where it's produced and what the environmental standards are and so on, and certain social impacts and so on, that's important. Well, now we start looking at deep sea mining. And this is a very important aspect for in the neck of the woods where I come from now, because all of those South Pacific islands are sitting with quite a vast offshore resources that could potentially mine, which is, again, a geopolitical issue. It's a bit of a race. There was a South Pacific summit last week, all right, and it was a real US-China competition around getting into the region. And the implications are, if you're going to real deep sea mining, that you don't need any environmental authorization, resource consent, as we call it in New Zealand, to do that, right? So there's real concern around how that is going to be done. Case in point is the Clarion-Clipperton zone. I don't know if you guys are aware of that. It's a 5,000 kilometer stretch on the seafloor, about 5.5 kilometers deep, about halfway between Hawaii and Mexico. And it's international waters, right? Doesn't belong to any country. Obviously, a sticky point for the US. China is looking at this with much interest, because what you see on this photo, what they call this mineral pots, they're about the size of potatoes. All right, and every kind of minerals that you can think of. And you don't really need to go dig it up, you just suck it up from the seabed. But this is one of the last pristine, biodiverse, because you can imagine around those pots over the millions of years, the biodiversity and has now evolved around those pots. It's, yeah, as I said, it's probably one of the last untouched ecosystems on the planet. So a real big concern how that's going to be dealt with. The reason why we're looking at those resources, again, this comes out of study out of Finland 2 years ago. And we'll get to the downstream implications. The point of that they make is recycling cannot be done if it hasn't been manufactured yet, right? So there's not enough stuff up there until recently. I'm going to touch on that later, which means that we will need to go and mine and produce those minerals. And what this is showing, as the grade of your ore decreases, right, coming to the left-hand side, means that we need more energy to extract the mineral. Also, what came out of the discussions in one session, at least yesterday, is we're dealing with databases that are somewhat out of date. This is one study where they said what the IPCC claims the energy and environmental footprint of solar PV, they might be underestimating those life cycle implications. All right, in terms of understanding what's happening, as the picture shows there around the mine. On the other hand, we've just did an LCA a couple of months ago on one of the solar utility scale solar farms that's now being built in Ontario, New Zealand. And actually, on the one hand, we might be underestimating some of the impacts. On the other hand, some of it, there's more efficient processes, especially around how the silicon wafers are cut, a lot less wastages. So there's some efficiency gains in the production of PV. And as you can see out of this graph, not unexpected, in terms of material intensity, it's largely glass, aluminium, steel, glass going into the PV modules, aluminium, steel into mounting structures. But that's not to say that other minerals, even those low quantities, that they're not important, right? It's even because it's quite energy intensive, as I said before, to produce those minerals. But it's sort of interesting looking at the clean tech. So what the graph on the left-hand side, it's just two metrics on the left-hand side, the global warming potential and cumulative energy demand on the right-hand side. As I said, overall, it's largely the bottom through the PV modules and then the mounting structure that's really important. Some sea freight, some road freight associated. Obviously, we need to replace the inverter after 15 years. But two things that come out is, as I said, more upstream energy efficient processes. And obviously the tech, right? 10 years ago, when we were looking at life cycle analyses of PV modules, we were talking about 20 years of operation. The guarantee for those PV panels are now 30 years. We had to replace the inverter every 10 years. Now we can replace it every 15 years. So in the context of our country, think about the greenhouse gas payback time, less than 1 year. Even if you consider the national grid, our national grid is now sitting at less than 100 grams of CO2 equivalent per kilowatt hour. So compared that to South Africa, where it's about 900 grams, if I'm not mistaken. So even bigger again. Well, to the top end side, because what effectively the solar PV farms will do in our country is it will displace combined cycle gas turbines. And you can see the paybacks now, less than half a year. The energy payback similar to this here. So the energy return on investment is the metric that everybody sort of uses. It used to be about 20, less than 20, 15 for PV. Well, we see that it's going closer to 14 now. Again, mainly to do with how much electricity is being produced over the 50 years, even in a country like New Zealand that doesn't have the solar resource compared to like South Africa. We just the last week completed for the offshore, one of the offshore wind projects. As I said, it's a gigawatt scale. Also, no surprise in terms of the material intensity, its foundation is going to be monopiles, so just pipes, if you will, driven into the seabed. So a lot of steel going into those, into the wind towers as well, and also obviously into the turbine itself. But again, all kinds of other materials, and as I said, in the middle there, those rare earth elements are it's a really key issue in magnets. And there's different. This one becomes a little bit more interesting because, as I said, of course, the energy that goes into the monopiles and the wind turbine, so on, is important. Those are the two bottom parts of that graph. But operations and maintenance is becomes an interesting one with this tech, because you're sending out boats quite regularly to do maintenance, and so it becomes quite fuel intensive. And so one of the key issues that this industry is looking at is, okay, we need to get better maritime fuels, or clean fuels. So yeah, this looks less great, so less than 7 years payback on it in terms of greenhouse gas emissions. But bear in mind that we're still going to be operating for 23 years. The energy payback still looks pretty good, and the energy return on investment is somewhere between 30 and 60. So yeah, so let's understanding the life cycle. So what else is some of the important issues? Is more transparency. Yeah. So as from the discussions that we had yesterday, we need to update our databases, but that means that we need more and better data out of our supply chains. So supply chain management that was mentioned earlier on becomes really important, and we now have a mandate in our country that you need to provide detailed information about the supply chain and where it's coming from, where the materials are sorted, processed, etc. And how is that done? Well, there's technology around that. Blockchain. I showed you the Brooklyn microgrid earlier on. That whole microgrid market is managed with blockchain technology. But blockchain is also being used as a transparency measure for supply chain management. There's certain challenges. We're going to have a link. I think the interesting one for me is the second bullet is blockchain. Depending on what blockchain tech you're using, it can be quite energy intensive, which is sort of ironic given that we're trying to manage energy systems. Second last bullet, also a hot topic in the research community, is about cybersecurity, as we not only using blockchain, obviously, but all of the other smart tech and IoTs and so on, communication technologies that we're using in making systems. Downstream implications, as this community will know, mentioned in one session in Australia, so solar PV panels that came to the end of the life, the farmers are using them for fencing. It's great. But they have now reached a point where it's about 450 million tons of end of life solar PV. Okay, so that's an enormous amount of waste that they now need to deal with, but it's typically we went to landfill sites. So bringing legislation, as you can see from this article, in New Zealand, we are introducing an import license, if you will, for the technology, so that we can track that technology, and whoever's importing it or installing it, the owners, it is their responsibility for responsible end of life management. And the same goes with batteries. Again, on the left-hand side, from the IEA report showing how much more batteries we're going to be needed going forward. On the right-hand side, what percentage of those batteries are actually recycled materials? Even going to 2040, it's still a very small amount for the different different materials in those batteries. And it's because our recycling rate or input rates has just been more or less stable. All right, so even though we're using more materials, there's more tech being deployed, it more or less bringing the same percentage of that material back into the loop. So what this is just telling us from a circular economy perspective, it's not actually happening. That is one of our biggest challenges over the next coming decades, because we're going to be sitting all over the world with the same situation that we're sitting in, as I've shown in Australia. USA is having a massive problem with landfill of end-of-life wind turbines, specifically in the blades. So I'm going to sort of end off this. So I think about Arteria and LPS, we've done some work in circular economy strategies that are being analysed, but it's not really comprehensive to clean energy transition. On the right-hand side there, we've had some initiatives from our battery industry groups to think about, as I said, import licenses for the batteries, and getting the institutional arrangements and so on into making it happen around the batteries, but certainly not comprehensive for the clean energy transition. So as we know, recycling is crucial, but we need a long-term strategy over the next 2 decades as we are transitioning. And what is really important for us in our part of the world, we are a small economy, our neighbors are even smaller, so we won't be able to do it without connected economies. All right, so we can get the economies of scale to make recycling affordable and close the loop, so to speak. Is that